And that'll be a focus for a couple lectures here, and then also Ian Groom's lecture when he guest lectures, looking at how perturbation methods of multiple scales can be used to resolve issues of resonance in oscillatory systems. So so today we're going to talk about forced motion near resonance. And the near should imply to you that now there's an additional small parameter in your problem that represents how far you are from that resonant frequency. So now if you force nearby to a resonant frequency, right? A typical resonance problem, right? Would be y prime prime plus y equals sine of t, right? So if you solve this in an ODE class, you get a exact solution that's going to involve functions of the form y equals a t cosine t b t sine t, right? That builds up over time. Okay. Now near resonance would be like if you have y prime prime plus y equals to sine 1 plus some epsilon t, right? So now your solutions are not going to grow indefinitely over time, but you are going to get some resonant response, okay? So rather than something like this, it's going to build up over time, maybe your solutions will grow to some value and sort of remain at some high amplitude amount, okay? But you're not going to continuously inject energy into the system that's going to cause the amplitude to grow, okay? Now, in a damped nonlinear oscillator, okay, that's forced near some resonant frequency, okay? The fact that you're not forcing right at the resonant frequency means that you're not going to have amplitude growth. And also the fact that you have damping means that you should expect energy to leak out of the system. You have some friction in a spring, some friction on the rope of a pendulum or something like that, okay? And so we're going to take, for concreteness, this nonlinear oscillator, y prime prime plus epsilon lambda y prime. That's going to be our friction term here, or damping, plus y plus now epsilon kappa y cubed, which is going to cause there to be some nonlinear response. You can imagine that if instead here we had something like a sine, which you get in a nonlinear pendulum, okay, this may look something like the expansion of a sine if kappa was negative in this case, right? The Taylor expansion of a sine. And so to order 1, the resonant frequency of this problem would be 1. And if we have something like cosine of 1 plus epsilon omega times t for t greater than 0, okay, and we have some weak friction, we have some weak nonlinearity, and we have some weak forcing that is slightly perturbed away from the resonant frequency. So we can vary epsilon to have, put these things all in the ballpark of each other. But as we shrink epsilon down to 0, right, this forcing term is going to go away simultaneously as it gets closer and closer to the resonant frequencies. Okay, so we should see some interesting effect because you're pushing it away from the resonant frequency. Should also grow the amplitude of these corrective effects. Okay, so here's our nonlinearity, and here's our forcing function. Okay, and we're going to take this oscillator initially to be at y0 equals 0 and initial velocity of 0. So all the motion in the oscillator is going to come from the injection of forcing. Okay. Now this is kind of a canonical problem. It's called the force Duffing equation, and some person named Duffing. Okay. And so this, yeah, I sort of labeled all those things already, so I'm not gonna rewrite what all those things are. Okay, all right. So now, if we want to build up to considering how this system is going to behave, okay, let's consider the simpler problem, right? I sort of wrote this down up here, but now let's write down a general forced oscillator problem. A linear oscillator with some arbitrary forcing. That's weak in this case. Now we can solve this. We get y is equal to epsilon over 1 minus omega squared cosine of omega t minus cosine of t. Okay, if omega is not exactly equal to plus or minus 1. Okay, so you get your forced oscillation, and then you have your natural oscillation of the problem, and those interact somehow. But notice that in the limit, as I take omega to 1, okay, I'm going to get something interesting happening here. And of course, I'm going to get like a resonant type solution like this. Okay, so as omega starts to go towards 1, the amplitude of the oscillation is going to grow, of course, because you're getting closer and closer to hitting this oscillator right at the frequency that it likes to oscillate at. So it's not going to dissipate that forcing. It's going to suck up that energy, and it's going to retain it, right? So you're going to grow the amplitude of this oscillation over time. So so then if omega is approximately equal to 1, right, the amplitude is stronger. And of course, this suggests us looking at a perturbative problem where omega is approximately equal to 1 plus epsilon omega, just like in our own problem. Okay, and we're going to take in particular omega not equal to exactly 0, and we'll take it not exactly equal to minus 2 over epsilon. Okay, as we'll see, because that would give us sort of special solutions. We get singularities in the formula that we have. If we then work out our solution in this case, our amplitude is going to be given by minus 1 over omega 2 plus epsilon omega, just using some trig identities, 1 cosine of 1 plus epsilon omega t. Okay, and so basically, as omega shrinks towards 0, then what we see is that the amplitude increases. Okay, and now in the special case where omega equals 0, remember that we have a true resonant solution, something like this. Okay, and all this buildup basically gets us to the point that for a resonant solution and for a near resonant solution, we should expect to see some buildup like this, okay, that we may want to track according to 2 time scales, right? Now, there's a short time scale here given by the oscillation, and there's a long time scale here given by the growth in the amplitude, right? So when epsilon t gets to be order 1, then the amplitude of our oscillation is going to be order 1, okay? So, so the amplitude of solution can be an order of magnitude larger than the forcing, okay? Now you say, well, I look at this solution and I really don't see any of that, right? I don't see growth in the solution. But remember, if you're doing all these things perturbatively, okay, as you start to build up your solutions, you should expect to see potentially terms like this leaking into perturbation expansions, okay? Just like we found when we sort of opened this chapter, that you're going to start to sort of inject energy into the system that's not going to dissipate because you're doing things perturbatively, because you're near resonant forcing. So that means you have to handle this somehow, okay? So how do we handle this, okay? Well, of course, we're in the realm of method of multiple scales, so we want to deal with a method of multiple scales, right? And as we've drawn up here, right, one of these time scales is going to be the relaxation of the amplitude, okay, which for a linear oscillator, right, it looks like there's not much any relaxation here when we solve the exact problem. But once we start dealing with nonlinearities, once we start dealing with friction and damping combined with resonance, we should expect to see these slow time scale relaxations as we see in a standard sort of linear resonant oscillator, okay? Secondly, there's the oscillation frequency, okay? So fine, so for the Duffing oscillator, remember the Duffing oscillator or equation, we're going to try multiple time scales, okay? One of these will be T1 equals T, the other will be T2 equals epsilon to the alpha T, okay? And like always, you know, you can always just try epsilon to the 1 and see if you get something sensible for your solution, right? Or you can do this and then look for a distinguishing limit once you do your expansion and start sort of cleaning things up, okay? So in that case, we're going to get some expansion dt1 squared plus 2 epsilon alpha dt1 dt2 plus epsilon 2 alpha dt2 squared y. Okay, then plus our friction term, epsilon lambda dt1 plus epsilon to the alpha dt2 y plus epsilon kappa y cubed is equal to epsilon cosine t1 plus epsilon omega t1. Okay, squeeze that in there. All right, and then of course we need to perturbatively expand y as well, okay? And we expect that near the resonant frequency, we should get some high amplitude solution, okay? Okay, so either where epsilon is approximately 0 or near 0, or potentially where as epsilon goes to 0. Okay. So we should expect to see that in our expansion. Y, as we expand it now, we're going to give it arbitrary scalings for the leading order terms. Okay. Epsilon to the beta, epsilon to the gamma, y1, t1, t2, and so on. So we'll take beta is less than gamma, okay? But I'm going to take beta to be less than 1 also, okay? And the reason I'm going to expect that beta should be less than 1, right, is because we're operating near the resonant frequency. And just because I'm forcing with some function that's of order epsilon, okay, because I'm going to start to engage the resonance of this oscillator, I should expect that the amplitude may grow to an order that's larger than the forcing itself. Okay, so that's the motivation for taking an arbitrary scaling here. Okay, so we'll see what that comes out to be.
Is there any reason why we're doing less than 1 as opposed to less than 0?
Oh, why I wouldn't expect it? Well, I mean, yeah, I guess it's covered under this heading, right?
Yeah.
But all I'm saying is that I expect it to be of higher amplitude than the forcing potentially.
Okay.
But this could include, yeah, you could have, you know, epsilon to the -1/2 or something like that. So it could grow quite large. Yeah. So this doesn't exclude that possibility. Okay, so let's sub it in. So if I sub this in, then I'm going to get dt1 squared plus 2 epsilon alpha dt1 dt2 plus blah, 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 so on and so on. Epsilon to the beta now. Epsilon to the beta, y0 plus epsilon to the alpha, y1, plus now epsilon lambda dt1 plus so on and so on. Epsilon to the beta y0 plus higher order terms plus epsilon to the beta y0 plus epsilon to the gamma y1 plus epsilon kappa epsilon to the 3 beta now. Now we get sort of an interesting comparison of powers plus some higher order terms that probably are not going to matter for our leading order expansion. Epsilon cosine T1 plus epsilon omega T1. Okay, fine. So let's group everything together, right? So a bit of algebra and we get epsilon to the beta d T1 squared y0 plus 2 epsilon to the alpha plus beta dt1 dt2 y0. So we get this interesting mixture of all these arbitrary powers. Epsilon to the gamma dt1 squared y1 plus some higher order terms plus epsilon to the 1 plus beta lambda dt1 y0 plus higher order stuff, okay, plus epsilon to the beta y0 plus epsilon to the gamma y1 plus higher order stuff plus epsilon to the 1 plus 3 beta kappa y0 cubed plus higher order stuff is equal to epsilon cosine T1 plus epsilon omega T1. Okay, so what's our leading order? Well, we made an assumption that probably beta should be less than 1, okay? So it should beat out our gamma, okay? Because that's the higher order term in our y expansion, okay? But also our time scale should probably be slower than the amplitude, of our leading order term, because that's the result of this resonant forcing. Okay, so let's start at order epsilon to the beta. That's going to give us dt1 squared plus 1 y0 equals 0. Okay, our typical sort of just nice linear oscillator. Y0 at 0, 0 is equal to 0, and y0's derivative at 0, 0 is equal to 0. Okay, so that's going to give us that y0 is equal to a t2 cosine t1 plus some shift in phase theta of t2, where a0 is equal to 0 in order to satisfy our initial condition. Okay. Now, to include the most terms at next order, okay, let's look up here, right? We're going to have some term epsilon to the alpha plus beta, okay? We're going to have some epsilon to the gamma term here. We're going to have some epsilon to the 1 plus beta term, okay? Epsilon to the gamma, epsilon to the 1 plus 3 beta, okay? It turns out if we take beta is equal to 0, okay, so we really do get this order 1 term to leading order, and gamma equals 1 in this case, okay? And then to assist in secular cancellation here, we want to include this term as well, okay? So remember, this term is cropped up in our other method of multiple scales problems and secular term cancellations, okay? So if we want to include that at next order, we should set alpha equal to 1, okay? So to cancel our secular terms, we'll also set alpha equals 1. So then we're just going to have a next order, right? Because we don't have any fractional powers, just order epsilon in this case. So we get a long expression that we have to do a bit of, differentiation, algebra, some trig identities. Okay, I'll just write that out. Okay, at order epsilon, we're going to get dt1 squared plus 1 of y1. This is the typical thing that happens. On the left-hand side, you have some linear operator acting on your next order term, okay? And then we're going to have some inhomogeneity on the right-hand side that could potentially involve secular terms that we'd like to cancel out. And that is how we pin down the amplitude of our leading order term, okay? So 2 d1 dt2 y0, it's going to be an inhomogeneous term, minus lambda dt1 y0, another inhomogeneous term, minus kappa y0 cubed, another inhomogeneous term. And now for the forcing, right? So our forcing term is going to be canceled somehow with our inhomogeneity from the lower order terms here, okay? So that's how we prevent ourselves from getting pure resonance that would just cause energy to build up in our system indefinitely, which we know should probably not happen, okay? So if I work all this out, right, remember back here, here's our form for y0, right? I'm going to have to do some differentiations and pairing up terms together. I get 2 a prime from this term here, plus lambda a sine of t1 plus this theta, this phase shift. Remember, theta itself is a function of t2 plus theta prime a cosine t1 plus theta in this case, minus kappa over 4a cubed 3 cosine t1 plus theta plus cosine 3 t1 plus theta plus now our forcing term cosine of t1 plus omega t2. Okay. Now remember, you know, you have a few choices as to how to express these periodic functions. You could use complex exponentials, and sometimes that's a bit easier than these sort of shifted trig functions. Okay, but we're using shifted trig functions here. You can try either and see which you prefer. We're going to separate now cosine t1 plus omega t2 is equal to cosine t1 plus theta minus theta plus omega t2. This, using a trig identity, is equal to cosine t1 plus theta cosine of theta minus omega t2 plus sine of t1 plus theta times sine of theta minus omega t2. Okay. And this will help us to remove the sine of t1 plus theta cosine t1 plus theta terms. Okay. Now what we want, I'm going to write out some equation now. We need that 2a prime plus lambda a is equal to minus sine of theta minus omega t2. And also that 2 theta prime a minus 3 kappa over 2a cubed is equal to minus cosine theta minus omega t2. Okay, because those are our resonant terms, right? Sine of t1 plus whatever shift, cosine of t1 plus some shift, right? I have to have these out of this expression here, otherwise I'm going to get resonance in y1, which I don't want pure resonance in y1. Okay, so from these and our initial condition, a0 equals 0, and assuming that our amplitude's going to grow over time using physical intuition, and theta 0 is equal to minus pi over 2, what we get is y is approximately a of t2 cosine of t1 plus theta of t2 to leading order. Okay, and so we need to solve this initial value problem now for a and theta, okay, to get these amplitude corrections. Okay, so to find a and theta, we would need to solve the initial value problem. And we could do that by investigating the steady states, okay, where a prime is equal to 0 and a goes to a infinity. If we look at this initial value problem, right, doesn't look like something we can solve by hand, okay? We're not going to be able to solve this by hand. So typically the way that people handle the Duffing equation is to do a steady state analysis of it in the phase plane, okay? The steady states, right, of this are going to be, you're either going to get 1, 3, 1 or 3, depending on which region of the domain we're in, okay? I'm not going to do that in detail right now, okay? But the basic idea is A is going to go to some steady state, and theta is going to go to some steady state value as well, okay? And in particular, sine of theta infinity is going to equal minus A infinity, okay? And so at the end of the day, we can get this equation for A infinity squared, lambda squared plus 2 omega minus 3 kappa over 4, A infinity squared is equal to 1. If we're just interested in positive values of A infinity, then we should expect at most 3 roots of this equation, right? This is actually a 6th order polynomial in A infinity, right? But we expect at most 3 positive and 3 negative roots, okay? And the negative root should be the mirror image of the positive roots, okay? So, so what we should find then, and I'll just sketch this out, is if we solve this for some value of kappa small, okay? So I think this is taking, something like kappa equals 0.1, okay? Or now let's just, I think actually we can take kappa equals 1 and lambda equals 1 because epsilon is our small parameter there. I'll draw out the qualitative diagram of the stability here. And there's 3 regions, okay? There's a region where omega is less than some value omega little m. There's a region between omega big M and omega little m. And then there's a region to the right of those, okay? And so what we find is, rather than me going through the solving all of this and getting these roots, I'll just draw the roots that you get if you solve this polynomial for its roots. There's this region here, which I'll call region 1, where we just have a single stable root, okay? There's a region here where you get this sort of bend back. Sometimes we call this hysteresis, okay, that results in bistability. This is going to be our region 2 here. And this will be our region 3 right here, okay? So here we have one stable steady state, okay? In this region, we have bistability. This is going to be our region 2. And over here, we have one stable fixed point, okay? So the cool thing about this is that if you're forcing this oscillator, right, you could imagine that, let's say I sort of turn up the frequency of the forcing. if I turn up this frequency high enough, I'm going to leave sort of the realm of the resonant frequency, and my amplitude is going to drop precipitously to this stable fixed point. Okay. If I then start to turn the forcing frequency down, okay, I'm actually going to follow the lower amplitude for a while, okay, until I leave this branch here and I jump up to the stable branch over here that ends up being the higher one, okay. So this tells me something physical about this nonlinear oscillator, is that there's a region of forcing frequencies where I could get either a high amplitude oscillation or a low amplitude oscillation, depending on the initial condition of the amplitude before I start that forcing. And there's this sort of unstable branch here. Okay. And I don't know how many of you have had, bifurcation theory, but, in our ordinary differential equations course here, we just talk about this kind of thing in the context of phase plane analysis. Okay. You can analyze the stability of these by just doing, a typical phase plane analysis. Gives the stability of the fixed points of this equation. Okay. And usually if you find some region of space where you have like, 3 fixed points or something like that, you expect at least one of them to be unstable. Okay. And so that's often the regions where you find bistability. Okay. So these asymptotics, right? They provide insight across a range of forcing frequencies, okay? And in particular, the bifurcation structure, okay? So this is something extra that you get by doing the asymptotics, right? Exact solutions may be so convoluted sometimes that they don't really give you this qualitative diagram of how a nonlinear system is behaving. Okay. Numerical simulations would be taxing because you would have to, pick all of these parameters and run simulations. And even then, you may not pick the right initial conditions in order to see these 2 different stable oscillations, right? Because in region 2, as I said, there's a steady state solution that's going to look like this, okay? This would be like maybe a plus, okay? And then a minus down here would be that I have some smaller oscillation, y, as a function of t. Okay? So depending on where you are, right, you're going to get these 2 different things. And oftentimes these can be difficult to just pick up if you're choosing random initial parameters, right? And you would need to know exactly where to look in order to find this, okay? So that is one thing that I think is pretty cool about asymptotics, is that you can unfold these sort of bifurcation structures, okay, with just a little bit of work, and by matching up sort of multiple small parameters in your problem. Because if you think about what we've done, right, we've taken the friction, the nonlinearity, the forcing amplitude, and also the near resonance correction to the forcing frequency, all to be of order epsilon. Okay. So we've taken 4 small quantities in our problem, okay? And by having all of those be weak, and by sort of matching our multiple timescales of approximation appropriately, we've unfolded this bifurcation structure of the Duffing equation, okay? So you can extend this to sub or super harmonic resonance, right? So if you force like a 2 pi oscillation at a period of 2 pi over n, or 2 pi divided by n, right? And in that case, you get these different sort of types of mode locking, okay? So if I force at a frequency that's like twice as slow as the resonant frequency, I should still expect some energy injection to build up. Also, if I force at a frequency that's like twice the resonant frequency of an oscillator, I should also expect energy to build up in that case. And so, depending on each of these possible forcing frequencies that you might have, you can get these sort of near resonance phenomena in the case of this and many other nonlinear oscillators. Okay, so I think that's what I want to say about Duffing equation. Are there any questions about this problem, this system, this approach, the choice of epsilons? Okay. All right. Well, I always run over, so why don't I end early today? And on Monday, we'll talk a little bit more about nonlinear oscillators. In particular, we're going to talk about nonlinear oscillators where you can asymptotically show the approach to a limit cycle, an example called the Rayleigh equation. Then I'm going to talk about something called Mathieu's equation, where we actually have time periodic coefficients of an oscillator. And I'm going to set up a problem that'll be on homework 5 for you on that. And then we're going to switch gears and talk about PDEs for a little while, method of multiple scales for PDEs. And then actually, I think quite a bit of the rest of the semester will be more focused on PDE problems. So, all right. So don't forget your project proposals due on Wednesday. If you're still kind of looking around for topics or need help kind of putting together a proposal, you can meet with me outside of office hours, or just meet with me in office hours on Monday or Tuesday. And yeah, homework 4 is due on Wednesday. So yeah, happy to answer questions about that too. So have a good weekend, and I'll see you all on Monday.
Thanks, Zach.
Thank you.